Let's talk about the elements that we will need to consider to implement this algorithm of bubble sort. We will use two libraries, the random library that we will use to sample between integer numbers, and it will be used only once to get an initial list that is unsorted. And we're going to use the pygame library to visualize the process. Keep in mind that if you already have a list, and if you don't want to visualize the algorithm, you just want the list, you don't need to use any of these two libraries. In the data definition section, we have in the screen a tuple that contains two integers representing the width and the height of the screen in pixels. The display is going to be the pygame surface, which is a class that is produced using the method setMode that receives the screen. setMode is part of the display sublibrary. EndBlocks represents the total number of blocks that we will have, representing therefore the number of items inside of our list. Maximum height will always be the second element inside of a screen, which is the maximum height that a block may have. W is set to represent a constant, the width of each of our blocks. This value is calculated by taking the total number of blocks and dividing 800 by that number. These values we should probably use as a screen at index 1 and this one as a screen at index 0. The data definition block represents the basic unit of information in this program. It is an instance of a class with the same name. The class block is created by passing to the constructor only the position in C, which would be the left to right direction. The position in Y is calculated by simply picking a random number that will represent the height, defined between 0 and the maximum height. Self.r starts at 0 because there is no rows. This value can also be eliminated, but because the block is technically a tile, I don't want to do so. Who knows, maybe in future implementations we'll decide to use it. X and Y are the coordinates that the pygame library requires to know where in the screen to place our block. Cell.x will be equal to the product of the number of column times the width that is a constant for all of the blocks. Cell.y will be equal to the initial position where the corner of the block will be. We'll see how, instead of using the top left corner, we'll use the bottom left corner of each rectangle. This one should not be confused with the height of the rectangle. The block's height is given by this line right here. This is simply the coordinate where the program knows where to start drawing the block. Self.rect is a variable that you may already feel familiar with. It represents an instance of the class rect and takes the position in the x-axis, the position in the y-axis, how far to the right we move, which is a constant w, and how far we move up. The draw function is a helper function or method inside of the class that has the simple job of updating the position of the rect component, because remember we are moving these elements within their list. Therefore, the position in C inside of the array of values changes. So this is updating the position of that square, and then we are drawing it using the rect component. To draw it, we use the draw sublibrary, rect method, and we pass the surface, which is called the display, the color of that rectangle, and finally the position and dimensions of that rectangle. That is a block. The next thing we'll do is to create a data definition for the aggregation of different blocks. How many depends on the parameter n blocks, the total number of blocks that we want to have. Here you can see that we are working procedurally because we are randomizing items. LOV starts as an empty list, and for every single integer that represents the position of each block from 0 to the number of blocks minus 1, because we start at index 0, we create a block and we append a block. So we end with a list of blocks with 100 items. This list of blocks is a compound data type. which means that we can use a template in order to tell other programmers and ourselves what's the best way to go through every single item inside. This is our template. The best way to visit every item in a list or traverse it is with a for loop that says do whatever you want to do, but do it to an item called the block. We are ready to start the coding process. Let's start by first creating a draw function. Normally we would need to create an update function as well, but for the first time the behavior of the algorithm is contained within the process of drawing. So we are not gonna separate this into different parts anymore. Down here we will start using a for loop that will visit every single block. So for j in, and we're gonna use range len, which is a way to transform the items inside of a list into integers, and we're gonna get as many of those integers as items we have in that list. There is another way to do this that most people recommend, and that is using enumerate. But for this particular implementation, I found it rather confusing, because what it is giving you back is a tuple, and then you're just decompressing that tuple to get two parameters, j and something else. J represents the number of the item in the list, and this underscore represents the actual item that you are getting, which is a block. But at this level, we don't need it. So I'm just gonna keep it like this. Feel free to use whichever method you feel more comfortable with. So we have a variable j. Now for every single block that we visit, we need to repeat the process. Now for every iteration, every pass that we make throughout the entire list, we need to visit every single item in that list. So we go for every single item in a range that goes from lov minus j. We determined that j had to have an effect bigger than 0, so we're gonna subtract 1 to it. Its effect has to be of subtraction. So by making j more negative, we accomplish the same effect as setting the value here starting at 1. Now the question that we need to ask is if the height of the block at the index I is bigger than the height of the block at the index I plus 1. If the answer is yes, then we need to swap. So we ask if the element I in the list lov has a height that is bigger than the element in the list lov at index I plus 1. If the answer is yes, we know we need to swap. So we apply a helper function that we don't have yet. Let's just make a wish for it, and it's gonna include I and I plus 1. That should do the switch. Then we are gonna manually ask to display as .field so that we can update the background color. Let's pick this one that is the same color as VS Code's background. And then we're gonna call for the draw function. This draw function is in charge of visiting every single block and calling the helper function for that block. Let's copy the template for the list of blocks. I copy line 38 and 39, and I just paste it here. I get rid of the comments, fix the indentations. There it is. And now I just need to call block.draw. Once I'm done, I know I need to call for that handshake that pygame does with the programming language that actually renders the screen. So I'm gonna call for the flip method. That should be it. Now the last thing we need to take care of is of that helper function. So let's define swap. Swap is, generally speaking, the process of taking an item A, taking it out and putting it in a safe place so that we don't erase it, and then taking an item B and putting it in the original container of A. Once we have B unoccupied, we take the previous A from the safe space and we put it in B. That's the swapping process. Because if we just try to put B in A, then A gets lost. So we need to store it somewhere. So we're gonna take the index A and index B that we received, that's what we're gonna call them, and we're gonna call a placeholder lov at index A. Then we take the element at position index A and we make it equal to the position to the item at the position at index B. Now we do the opposite. We take the element at index B and we're going to make it equal to the placeholder. This is the swapping. However, there is one last thing we need to do. We need to also reflect the changes in the X variable for each of our blocks, because otherwise the rec component or hitbox that defines the position of those squares has not been updated. So we need to do it manually. Let's start with the index A. The position of that index A, which used to be B, is now going to be the position that it has in the list now, multiplied by the width. And the same happens with the object at index B. Let's run this program and let's see if it works. There it is. Now the screen is closing once the program is done, so maybe it's a good idea to keep it open. So if I want my program to stay open once the initial sorting process is done, the only thing I need to do is to incorporate an infinite loop that calls draw forever. But now we're also going to listen for an update function, because we want to make sure that we are able to close the window if we decide to do so. So we call the update, and for every event in the list of events of pygame, which we can get using the get method, we ask if the event is of type quit, which is a constant that pygame has. If the answer is yes, we call the quit again, but this time as a method. That should do the trick. Let's run it once more and let's wait until the sorting process is done. Notice that I am not able to move the window. And once it's done, I have the final result ready for visualization.